So work through this, and if we've got time at the end, maybe we could look at the exercises on that chapter, or certainly in the second session today. Some of those. Here. Pen. So first of all, you got to know the statement of Lagrange's theorem, at least. Yeah. And so the first part, has everybody got the exam? Yeah. The question 3a. State Lagrange's theorem on the orders of subgroups of a finite group G. Okay. I mean, there are a few different ways you might present Lagrange's theorem. But here, so if G is a finite group, now with your statements of theorems and your definitions, you just want to be trying to be, really hit the nail on the head. Don't leave any ambiguity. Try and just state very clearly and simply what the result is. And don't be afraid to use it. This isn't a case where you have to write it symbolically or something. You can just write it out in English, but just as long as you're clear. So if G is a finite group of order n, i.e. order of G is n, and H is a subgroup of G, so it's certainly true that H is a finite group, yeah, because subgroups are, first of all, subsets. If G is a finite set, then any subset of it is going to be finite. And to justify that, really, any further. And H is a subgroup of G. So now we come to the nub of the matter. Then the order of H divides n. That seem okay? I don't think I've left out any aspect of it here or anything. So if you've got a finite group and there's a subgroup, its order must be a divisor. Whereas the implication does not go automatically in the other direction. Just because you're looking at a divisor of n, factor of n, doesn't mean there is a subgroup of that size. That was the question that we were dealing with, of course. So that would certainly get full marks there, that kind of statement. And as well, when you're stating statements, theorem statements tend to be in the form of an implication. If this is true, then that is true. So certainly make sure you get the direction of the implication right. Don't leave any kind of mix-up or vagueness about, what are the conditions and what's the conclusion. Always be, when you're rereading and checking things, make sure that your answer is really nailed that on the head. Okay. So and in part B then, part B is a multi-part thing here, and this is basically stepping you through the proof of Lagrange's theorem. I mean, a tougher question might have just been proof of Lagrange's theorem, right? But this gives you a little bit of structure, and it's pointing out the kind of things you should be talking about in the various parts. So 1, 2, 3 are various kind of preparatory results, and then part 4 says show how they can all be put together to prove Lagrange's theorem. So the proof we did of Lagrange's theorem uses the language of cosets and so on. So state the definition of the left and right cosets of H in G. Okay. So again, this is a definition. So you just be looking to state very clearly, don't leave anything ambiguous at all, what a left coset of H in G is. Okay. So a left coset of H and G. Well, first of all, what kind of thing is it? It's a subset G H of G. So that's true. It's a subset. And how is it defined? A left coset of H and G um, defined by subset little g times h consists of every product little g times a little h as h ranges over, little h ranges over the elements of capital H. Okay, so proof H, where G is some element of G. Okay. Does that pretty much define what a left coset is? Subset of G, given by that definition. I mean, you could word it as the left coset of H and G generated by little g or associated to little g, but that's clear in the way I've written it out there. And because we've just said where little g is in G, so there's no restriction mentioned on that there. So these clearly, you can clearly define such things for any element little g in G. Okay, that's the left coset. The right coset, a right coset, similarly defined, but with the products the other way around. So i.e. right coset, normally write like this, capital H little g, that's the set of every product little h times a little g, or again the little h ranges over the circle h. Is there anything more to say just on the definition of cosets? I don't think so. I mean, there's only 2 marks going for that part, so they went ahead there pretty much. Okay, so part 2 is the key thing about cosets. So we focus on left cosets, and this question is asking you prove that the 2 left cosets, G1H and G2H, are either equal or disjoint. And this is the key fact we need in order to prove that the cosets partition G. Remember, one of the ideas in going for proof of Lagrange's theorem is that the left coset EH, so H itself, then you've got other cosets, other left cosets of H and G, but the point is they partition G. So these different cells do not overlap. Okay. The same coset might be represented by many different representatives, but if you replace this little G1 with another group element in G, either you're going to be looking at exactly the same coset or you're going to be looking at it completely disjoint. You never get that it shifts so that half of it is still in here and half of it is over here. And that allows you then to count the number of elements in G by counting up separately the number of things in each cell and adding the results. Whereas if they did have non-empty intersections, you couldn't add the things in each cell and add them all up because you'd be double counting anything that appeared in an intersection, or triple counting, or quadruple counting. So this is the key part of this. So, okay. So we should let G1 and G2 be 2 elements in G. No restriction on that. We're not saying that these are definitely assumed to be different elements. G1 and G2 might just be 2 names for the same element. Okay, now we're trying to prove that they're either equal or they're disjoint. How might we broadly, overall, approach the proof of that? Slightly tricky because you're trying to prove an OR statement. So there's not one single conclusion you're trying to get to, because they're either going to be the same or empty. So we're not going to be able to definitely prove that G1H is definitely equal to G2H. And neither are we going to be able to definitely prove that G1H is disjoint from G2H. Because we don't know what G1 and G2 are. Maybe the two left cosets are the same, maybe they're disjoint. But we're going to try to prove that it must be one of those two possibilities. So any thoughts just on how, given the structure of the two statements, G1H equals G2H, or G1H intersect G2H is empty? Thinking about proof strategies for this. And also, you know, we did a lot of kind of meditating on this kind of in the number theory unit last year, thinking about, you know, what approaches are good for trying to prove things. And it's not relevant here, but there were occasions when we'd switch from trying to prove an implication to proving it's contrapositive, sometimes because the way the statement was stated originally, it was kind of, both parts were kind of negative things. You know, the things, you know, the condition might have been, if this is prime, then something else is prime. But those two statements are kind of, you know, well, if something is prime, you know it's got no factors. So it doesn't give you things to build an argument with, because it's a negative statement saying there doesn't exist factors of a certain kind. Whereas when you take the contrapositive of such a statement, so the original statement is, if this is prime, then that is prime. Then suddenly the contrapositive becomes, if that is composite, then this is composite. And that's kind of easier in some ways to get a hold of, because the condition that you should assume that that is composite, that gives you something. If you assume it's composite, then okay, there must exist two non-trivial factors that multiply together to give the number, and I can investigate those factors and try and build something. And that's maybe those kind of considerations are relevant here, not strictly due to contrapositive, but because one of the statements in the OR there is a negative statement. It's saying there's nothing in the intersection of G1 and G2. Well, if we assume that, it's going to, you know, that doesn't give you anything to grab a hold of and so on. So I just, well, I think here is, you know, maybe, perhaps, G1H intersect G2H is empty. If that is the case, it's certainly true that that OR statement is true. Yeah, because A or B is true if one of the parts is true. So if these two did have an empty intersection, then you wouldn't have to prove it. And the result is true. So we only have to actually prove something if that isn't the case. Does that make sense? Yeah? So if they are disjoint, you're finished. There's nothing more needed. So what is needed is if so assume on the other hand, let's say that G1H intersect G2H is not equal. It's not equal to the empty set, so there is something in the intersection. Now what are we trying to do? Now we're trying to build an argument that finishes with the statement. Well, what statement do I want to finish with here in this part?
G1 intersection does have.
Well, that's what I've just assumed.
Yeah,
Where do I want
proof that there isn't.
Sorry?
Never.
The G1 and G2 aren't equal.
Are equal. Yeah. But G1H is equal to G2H. Wherever possible, always be looking to where you can identify what the destination is. Because then, you know, you can't really go anywhere unless you know where you're trying to go, yeah? So we're assuming that there is a non-empty intersection and we want to conclude this. Okay, well, the obvious way to roll this forward is to name one of the things that is in the intersection. Because this is saying there is stuff in the intersection. So we can say let an x be an element of the intersection, G1H, G2H. And then that can be rolled forward immediately as well, using the definition of the left coset, which we've just gone to the trouble of defining a moment ago. I.e., there will exist two elements of H, a H1, H2 in H, such that the X is equal to G1, H1, and that is also equal to G2, H2. Because that's what it means for X to be in the intersection of the two left cosets. Now, what's a general principle of proving that two sets are equal? How do we normally approach that? So forgetting about anything specifically about Greek theory or that. If we're demonstrating that this set is the same as that set. The normal way to approach that is to prove that each is a subset of the other. So you show everything in the first set is contained in the second, and vice versa. Everything in the second is contained in the first. Okay. So I'm going to want to be able to start with the general element of the left coset and conclude that it's actually also in the other left coset, and then do the vice versa bit. Okay. So if I consider a typical element G1H, which is an element of this left coset, how can I argue that it's also, this element is also present in the other left coset, G2H? Well, it's got to come from what we assumed. Is there some way that I can take this information and reach a conclusion that this element, G1H, is also present in the other left coset? Well, to prove it is in the other left coset, you're going to have to be able to write it as G2 multiplied by something in H. So we want to get rid of this G1 somehow, and hopefully replace it with something involving G2. See, we've got up here an equation between G1 and G2. Okay, there's other factors around. But we're in a group, remember. Everything is inverses. So we could take this equation and make either G1 or G2 the subject of that, or G2 equals that. So see, this equation is equivalent to either saying G1, so if I multiply both sides on the right by H1 inverse, G1 is G2, H2, H1 inverse, or and I can also write it as G2 is, if I multiply both sides on the right by H2 inverse, G1, H1, H2 inverse. Inverses exist physically. I won't need to specify that all the time because we're in a more advanced question now, so just kind of assume basic Greek ideas. But these equations allow you to replace G1 with an object of the form G2 times something in H, and similarly replace G2 with G1 times something in H. So G1H, this typical element of the left coset G1H, can now be expressed as G2, H2, H1 inverse H. But you see, this triple product here is certainly an element of H, because H is a subgroup. Yeah. So this is an element of G2H. Since H is a subgroup. Yeah. So i.e. G1H is an element of G2H. And so the left coset G1H is contained in or equal to the left coset G2H, because everything in G1H is also present in G2H. So we took a typical looking element from G1H and demonstrated that it was equal to G2 times something in H. Therefore, it's in the left coset. And similarly, you can go the other way around. So also, a typical G2H in the left coset G2H can be written as, sorry, because I declared the endpoint, I'm having to shrink my writing a bit here. So a typical G2H can be written as G2H, so this is G1, so what is it? G1, H1, H2 inverse times this H, whatever that is, and that is an element of G1H. Okay, we've made the point because H is subgroup, well, don't have to repeat that here. So i.e. the left coset G2H is contained in or equal to the left coset G1H. So both sets are subsets of the other one. How can that be? That's basically the definition of set equality. Yeah, two sets are equal if and only if they contain each other's elements. So you're now justified in saying that the two sets are equal. Now that looks like a proof in some ways that we've definitely proved that G1H is equal to G2H. Remember I said we shouldn't expect to be able to do that because G1 and G2 are meant to be just general choice for pair of elements in H. They might give rise to different cosets. But we haven't reached this as a definite conclusion. We've reached this as a consequence of assuming that they were not disjoint. So if they're not disjoint, they're equal. So that means there's only two possibilities. They either are disjoint or they're equal. Yeah? So if they're not disjoint, they're equal. So we have in fact proved the required force. So we can conclude that they're either disjoint or equal. So just emphasize this here in this argument up here. So we assumed that G1 intersection G2 is non-empty, and then we got, as a consequence of that, we got that they're equal. Yeah. Not that we proved this without any assumptions. Now, it did occur to me maybe we should start talking about partitions and stuff, but you see, in part 4, it's asking you to how do you put together all these little bits to prove Lagrange's theorem. So that's where we'll basically discuss that idea of the picture. So we won't need to mention that at the moment. So is that okay? Any questions about that? So remember, if you're in an exam situation, just keep your head about you when faced with these little proof tasks. Always, try and operate these principles that we identified last year and continue to use this year. Look for how you're going to structure the proof overall. Typically, you'll know what the beginning of the proof is, what the assumptions are, the conditions. Typically, you'll know what the desired destination is, and you're looking to bridge that gap by either rolling the conclusion backwards or rolling the assumptions. Okay. Part 3, prove that all cosets of H and G contain the same number of elements. Okay, this is key to showing the divisibility. Remember the basic principle? Well, we'll discuss that in chapter 4, was just to count the things in G by counting the things in each cell and adding up to the sums. Well, if we know then they all contain the same number of elements, and one of them is H itself, then the total number of things in G is just the number of cells times the number of elements in H. So therefore, H divides the order. That's the argument of the proof. Well, we need to know that they all have the same number of elements. So one of the cosets is H itself. Remember, we define the cosets as subsets of G. The subgroup H is a perfectly good subset, since H is equal to the coset corresponding to the identity element. So when you multiply the identity element by everything in H, multiplying by the identity doesn't change anything. So you've still got the subset H. So we will prove that the size of any coset is equal to the size of H for all choices of representative of H. How will we do that? Well, common way, the more or less the default way for demonstrating that two sets of the same size is to set up a bijection between them, is to identify or define a definite mapping of the elements from one set to another. And if you can prove that the mapping is 1-to-1 and not 2. So then that mapping is a pairing of the elements from the two sets, one from one set, the other from the other set. You're pairing off the elements, and you're doing so in a 1-to-1 fashion. So everything only features in a pair once, and also in a surjective pattern. So everything from the second set is used in the pairing, and that is the principle. Using that, you can conclude that the two sets are the same size. Okay, so we define a mapping. So then the problem is, what's the mapping from so to choose a direction that you're going to go in. Okay, so what's the mapping? That's the problem. We're not talking about homomorphisms here, just some kind of mapping of the elements of one set to another. And the problem you've got to get over is that between any two sets with elements in them, two non-empty sets, there's a huge amount of mappings between them. The total number of mappings will be something like, it'll involve factorials based on the number of elements in the first set. So generally there's plenty of mappings from one set to another. So we got to uniquely define one, and then we can show that that one mapping is injective and surjective. So what's the mapping going to be? Well, in order to define the mapping, we have to define what value it takes on a typical argument. And a typical argument is going to be an element from H. So this is a moment like where I hold a gun to your head and ask you, what's the answer? There really is only one possible. Well, okay, there's a few different possible things to try, but there's one clear.
The identity. It's always the identity when you put a gun to your head.
That's when that was if I was asking you to name a particular element. Yeah, the identity is really the only special element in the universe of all groups. But here I'm not asking you to name. Well, okay, I'm asking you to name a particular element, but you see, the H could be anything from the little h could be any element there. And if you were giving me the identity, here's the answer, you'd be then defining the map as sending everything to the identity. It's certainly not going to be injective, because you're collapsing all the elements down onto one.
The G of H. It's like anyone G with a little H.
So G. So see, in this equation now, the little h is no longer around. The little h is a typical element here. For the purposes of this equation, little h is a particular element. Yeah. So yeah, I mean, it's this little g times that little h. That's certainly an element of this coset because it's little g times something. And it'd be perverse to define it to be any other element. Because you're trying to associate an element of the coset with an element of the subgroup. But by definition, the elements of the coset are little g times something from h. So you'd be making life complicated if you were going to mix it around a little bit. If you're going to not have this h appearing here, if you're going to have this little h, or I mean, you possibly could have h inverse here. That would still be setting it up in an injective way. Or you could also have h multiplied by any other particular named element of h. But again, that would be needlessly complicated. This is the one map that stands out between these two. Okay, injective, surjective. Well, I would say it's clearly surjective, since GH consists only of elements of the form G times H, for some H and H. And you've got all the H's, all the little H's available to you, because you're defining a mapping from the set, little H, from the set H. You know? But to be honest, if I was marking this, I'd just accept the statement that it's clearly subjective. I would accept that. You know? It's not like if I give you a typical element from here, there's a big problem about searching for, oh, what's the correct H that gets mapped to that element? That's not a question that needs answering, really, because if I give you a typical element from here, I kind of have to give it to you in the form little g times something from H, and then this is clearly the element, little h that gets mapped. Yeah. So it's clearly subjective. Maybe the only thing to prove is that it's injective. So suppose phi of G1 is equal to phi of G2. This would arise if it were not injective. If it were not injective, there would be two different elements, G1 and G2, that took the same value. So we'll investigate that, i.e. G1H is equal to G2H. Could that happen? Could little g1 times h be equal to little g2 times h? And that's the definition of the value of phi on these two elements. Well, what can you conclude from that equation? Just using basic group idea.
G1 and G2 are equal.
Yeah.
The same.
The same, yeah. So you get just by multiplying both sides by h inverse. I mean, I'd accept, well, yeah, G1h inverse equals G2h h inverse, i.e. G1 equals G2. So that proves that it's injective. The only time you can have the same value being taken on two elements is if they weren't really two separate elements. You're just mentioning the same one twice, i.e. phi is injective. So hence, the order of GH equals the order of H, since phi is a bijection. So that's like if in some ways that statement is like a result about finite sets. Finite sets have the same order if there exists a bijection between them. For infinite sets, this becomes the definition for what having the same order means for infinite sets. Okay. When early mathematicians started kind of making rigorous their talk about infinities, you know, you can talk about the infinite set of integers, and then the set of even integers is also infinite. but it's a subset of the set of all integers. It's a proper subset because it's missing all the odd numbers. So are they of different size? But actually, there exists bijections between them. You can set up a bijection from the integers to just the even integers, and it'll be 1 to 1 and on 2. So that's what leads us to say that those two sets both have the same size, even though one set is missing loads of elements that are present in the other set. So for infinite sets, this is no longer a result about infinite sets. It's the definition of what it means for infinite sets to have the same size. It's the existence of a bijection between. But for finite sets, it's a way of proving that the finite sets have the same number of elements. Prove it, establishing a bijection between. So is that okay? Right. Okay. So question 4: show how it all goes together to prove the Lagrange's theorem. Okay. So I would literally sketch this picture, and then just talk about the picture a bit. And as long as you mention a few key words and make a sensible description, you will get the marks. How many marks are going here? 6 marks again for explaining how it all goes together. So not a reasonable discussion. So it's the fact that they partition G comes from part 2. Yeah. So the collection of cosets. So this is the set of GH where G goes over G. Collection of cosets actually partitions G by well, let's say since every element of G is contained in a coset, how do you prove that? Which coset is little g contained in? Here's an element of G. Which coset contains little g? It's a gun to the head moment, I guess.
Yeah.
Which left coset contains the element little g? The system of left cosets is, every left coset is something from the group G times H. So it's got to be this one, isn't it? So that's an element of G. It's in the coset represented by itself, yeah. Since G equals G times the identity, and the identity is in H. The identity is in a sub. So it's certainly true that everything in G is contained in one of these cosets. And different cosets do not overlap. That's by part 2. Is that part 2 we proved? Yeah, part 2. 2 cosets are either the same or they're disjoint. So different cosets that are not the same, are completely disjoint. Okay, so that sets up the partition. That's the 2 points about partition. A partition of a set is a system of subsets which covers the whole set. So every element of the whole set is located somewhere in this picture, and the different subsets do not overlap. So then we can just describe this counting principle. So to count the number of elements in G, we can add up the number of elements in each coset. If you've got some kind of clear description of this process. So the number of things in here, plus the number of things in here, plus the number of things in here. But by part 3, we proved these sets all have the same size. But by part 3, each coset, each left coset has order of H, whatever that is. So that implies then that the order of G equals, well, you could just say number of left cosets. Number of left cosets times the order of H. So that gets you the divisibility. The number of left cosets is clearly an integer. It's just a count. Or you might, I mean, it might be slightly better if you use the appropriate notation where square brackets G colon H, index of G, the index of H and G is the number of cosets. So just some nice description of that basic accounting argument. This is an example as well where it's best to describe this in English, I think. You know, it'd be a struggle to turn this just into a symbolic argument. It's just simpler and more direct. And, you know, a better way to demonstrate your understanding is just giving clear descriptions. Okay? Because underlying it is these clear, simple principles of this basic counting argument. But that would, I think, get all those marks, show how parts 2 and 3 can be used to prove Lagrange's theorem. Yeah, we've done it. We've mentioned partitions. And now I need to be somewhere. So it's 12:48, so we might finish just there. But in the second session, well, we'll deal with part C, and then we'll dive into some of the exercises in the cosets Lagrange's theorem chapter. And you know, if any questions occur to you in the meantime, by this afternoon, please bring those along.